Konnichiwa, Shalom, Bonjour, hello. When humans greet each other, we say hello. We wave, we shake hands. It would be odd if we greeted each other by throwing an apple, or whistling a show tune, or doing a handstand. Every language and culture has a way to greet another person, and a way to communicate with human language. And we learn this at a very young age. It makes it easier for people to work together and share information. It's the same with machines that we've built and the Internet of Things. We have a language and guidelines. There are millions of computers and sensors, actuators, systems on the Internet. And for all things to communicate, we need a shared language and rule set. A shared language and rule set allows quick and efficient communication between things using less programming, power, memory, and data transmission. When people talk to each other, we call it language because we use our tongues. When machines talk to each other, we call that shared language a protocol. Previously, in transports, we talked about how to get your device onto the Internet: power, distance, and bits. Now, transports are the physical and wireless means to get data around, how to get data from here to there and back again. But transports often are not structured. Your data shows up in a pile of bits. You may not get your data in order, correctly, or even at all. On top of the transport layer, we can add another level of quality assurance: the protocol. A protocol can be thought of as that language between each machine to machine. It's what they use to talk to each other. Protocols don't deal with the messy business of moving bits to and fro. They are a higher level set of rules that the machines use to talk to each other. Chances are you're familiar with HTTP. But even if you're not, you've seen the letters at the beginning of every website. HTTP stands for Hypertext Transfer Protocol. It's used by the Internet to send website data back and forth. Note that you may connect to the Internet using Ethernet at work, Wi-Fi at home, or cellular on the go. But the HTTP part is the same for every website. HTTP is stateless, so you have to have a connection per data transfer. One connection for every time you want to write data, one connection for reading. HTTP is optimized for huge amounts of data, such as those used by websites. And it can be used by IoT connections. But it's not lightweight, and it's not that fast. Another problem with HTTP is it's pull only. So let's say you have an IoT device, an Internet of Toaster. This toaster is connected to the Internet and can send you toast updates, as well as have its settings managed securely online. With HTTP, your toaster can easily send data to the server whenever it wants, so tell you your toast is done, by connecting and submitting a REST PUT request. But if it wants to pull data from the server via a REST GET, it has to constantly connect and ask, any updates to the toast darkness level? What about now? Anything now? Which is really data and time consuming. Pull requests are either slow, because you're only checking every few minutes, or data and power intensive, because you're checking constantly. Let's review. HTTP is a synchronous protocol. This means the client has to wait for the server to send the data. It's a one-way street. Only clients can make requests. It's a one-to-one protocol, one client and one server and one request at a time. It's data heavy, filled with headers and rules. Now it's time to take a rest. REST stands for Representational State Transfer. It isn't exactly a protocol. It's more like a concept and architectural style that works for IoT. But it's based so heavily on HTTP that the two words are used interchangeably. REST is a well-established standard for transmitting data, and it's very internet-friendly. So if you're online, just about every web service uses REST both internally and externally. And every modern computer and programming language has REST API support. So it's very fast to get started. And if your device is going to talk to public internet utilities like If This Then That, Facebook or Twitter, etc., it will need to use REST. There are 4 ways to move data around using REST: GET, to request data; PUT, to send data; POST, to create data; and DELETE, which does what it says. Every web browser uses these commands to get and put the data that you use on the internet. And the data you get, put, post, and delete is stored in buckets called resources. The names of these buckets are also known as URLs, Universal Resource Locations. So let's say you want to query the Adafruit Twitter account. You can go to the twitter.com server using HTTP, using this URL, and then request the Adafruit resource like this. This will give you a huge amount of data, but you can drill down by adding more slashes and subcategories. So to read the post with our video visiting the NYC Formula E Series race, go to this URL. Now, that big long number is a unique identifier for the tweet. And what makes this URL RESTful is that each slash section gets more specific. Twitter, then the Adafruit account, then the statuses, and finally the unique status ID. While you could, in theory, parse a web page's HTML via your device through a REST query, it is a hairy and unpleasant business, and it breaks very easily. So instead, most services provide a REST API, which is simplified and machine-friendly. In those cases, the data is usually transferred via JSON or XML, but still using HTTP. Since we are using HTTP, the connection does not have state. The client connects to the REST API when needed, transferring data to and from the resource, and when it's done, it closes the connection. On one hand, this is nice because you have a burst of data transmission and then a disconnection, so the server doesn't need to hold the connection open. But the downside is you have to set up and tear down the connection each time, and that can take up a lot of time and a lot of data. XML stands for Extensible Markup Language. XML is a markup language much like HTML. XML was designed to store and transport data for machines. It is designed to be self-descriptive. In other words, when you look at it, it should be clear what it is based on the tags you define. But XML has fallen out of favor due to its parsing complexity and verboseness. These days, you'll see JSON most often. JSON stands for JavaScript Object Notation. It is a lightweight data interchange format. It is easy for humans to read and write, but designed for machines. And despite being based on the JavaScript programming language standard, you do not need to use JavaScript. You can use any programming language. It is easy for machines to parse and generate. XML is a markup language, and JSON is a way of representing objects. Generally speaking, JSON is preferred for IoT applications since it can self-describe and is more programmatic, whereas XML was made for document markup like HTML. But you're probably going to see both. For example, let's look at a public JSON API. There's not a lot of public APIs out there. Most of them require authentication, but GitHub has some public data available. So go to this URL. Here's what you'll get. Of course, some dates and numbers may vary. As you can see, the JSON data is very structured, but pretty simple. You can see the location is a string, New York City, but the number of public repos is a number, and other entries are URLs of their own, maybe Boolean values, etc. Since JSON is text-based, you can really toss whatever data you like in there. If you need to store binary data, you'll need to textify it somehow, maybe using base64 encoding. Well, compare this later to Mqtt, where the data is not text-based, but raw binary-based, and so it gets parsed however you like. The URL itself can end up being a data transport of its own. For example, Yahoo's Weather API has URLs that look like this. The JSON data looks like this. Now, if you write the URL to have format equals XML, you'll get the XML output. You can see that the data is the same, but the format is a little different. If a web service or API supports REST, it's called RESTful, and that way you know it sticks to that common architecture, and that means your programming language can easily work with it. But why use REST? Well, REST uses HTTP, so any device that's on the web can use a REST API. And many applications for IoT devices are about the state of the device, and that's why REST is used so much. For example, if you're a light bulb, your state is whether you're on or off, and REST allows easy modification of state, so you can send a command to post data and change the light state and then get the light state. In this case, REST and your programming language easily model the device that you're trying to control. Okay, so we're done. This solves everything for IoT. Just use REST and that's it? Well, not so fast. In fact, REST is part of the problem. With REST, it's all request and response. This means every time you want to do something, you need to request it and then get the response. And it can lead to a ton of requests, lots of data usage, battery drain, and slow data transmissions. Surely there's a better way. As you've seen from the transports video, some of our transports like cellular or LoRa, you end up paying per byte, per message, or working with a very restrictive bandwidth. In those IoT transports, you'll want a simple and lightweight protocol with push and pull. Let's look at a few more options. Mqtt, which stands for Message Queue Telemetry Transport, has become the most popular and essentially the standard IoT protocol. Note that even though it is called Mqtt Transport, we'll be referring to it here as an IoT protocol since it does more session management than data transport. One confusing thing about the name, it does not really queue messages. It's more of a store-retrieve model these days. And that's why you may see it just called MQ Telemetry Transport. Mqtt is an open, royalty-free, and an OASIS open standard as of 2014. Mqtt is a publish, subscribe, extremely simple, and lightweight messaging protocol. It is designed for constrained devices in low bandwidth, high latency, or unreliable networks. The design principles are to minimize network bandwidth and device resource requirements while also attempting to ensure reliability and some degree of assurance of delivery. These principles turn out to make the protocol ideal for the emerging machine-to-machine, MTM, or Internet of Things world of connected devices, and they're also good for mobile applications where bandwidth and battery power are at a premium. Mqtt was invented by Dr. Andy Stanford Clark at IBM and Arlen Nipper of Arcom Eurotech in 1999. It was developed at IBM in the late 90s and used to link oil pipeline sensors with satellites. The oil pipeline sensors and controls were not high speed, did not require a lot of data, and of course they were not near infrastructure. The up and down link used satellites that would move in and out of range, so HTTP would have been a very bad protocol to use because it requires a durable underlying transport. Instead, the oil pipeline network needed something more flexible and understanding of failures and dropouts. One interesting piece of Mqtt is that the protocol manages messages asynchronously. That is, the server broker in an Mqtt network can hold and forward messages from client to client. So if one gets disconnected, it will be able to fetch the message when it reconnects later. To keep things simple and allow bidirectional message passing, Mqtt uses a publish and subscribe model. Mqtt is a simple and well-designed protocol, and it turns out that the same protocol used for oil pipeline sensors and satellites is great for use in IoT. It's extremely simple and lightweight. Connecting to a server only takes about 80 bytes. You can stay connected all the time and send 2-byte ping packets every few seconds to verify connectivity, or connect once in a while to manage messages. Every data publication, pushing data from client to broker, and data subscription, pushing data from broker to clients, is as little as 20 bytes. Publication to subscription delay is instant. The connection is a single socket, so overhead is at a minimum. This makes connections and data super fast, and that's why Facebook uses it for the billions of people who use Messenger on mobile. Just like REST has text-based URLs, Mqtt has text-based topics. And like REST, Mqtt can manage arbitrary data payloads. You can send text or binary, a photo for example. As long as the clients can parse the data, you can use it. Basically, any packet of data up to a theoretical max of 256 megabytes, although in reality, most brokers and clients don't expect more than a few kilobytes of data per packet. Unlike HTTP, there isn't any big build-up and tear-down overhead for every request, And we can stream data in and out of multiple topics quickly and easily. This makes it easy to adapt to any transport since there are no underlying layers that you have to depend on. And full MQTT clients can fit in microcontrollers with as little as 32K of flash and 2K of RAM. MQTT can run on top of any kind of transport, whether it be a mesh network, TCP/IP, or Bluetooth. But if you're using Bluetooth, XB, LoRa, or any other non-internet connected protocol or device, remember, you're going to need a gateway to get data to and from the internet. Let's get into the details of MQTT. MQTT has some terms that make it easy to remember what does what. There are two types of players in an MQTT network, the broker and the client. There's only one broker, but there can be multiple clients. The broker is considered the reliable one in the network relationship. Even if the connection goes out, the broker is expected to be available whenever the transport is up and running. The broker gets all of the published messages from the clients and then stores them in a database or just in memory. The broker then delivers the messages to the subscriber clients. In general, the MQTT broker is not what we spend a lot of time engineering, as there are many great free broker softwares, as well as broker services you could pay for that will do all the management for you. The part that you will be most involved with is the client. That's your application, whether it be a sensor, robot, or toaster. Each device you design will come with its own MQTT client. Whenever there's a reading to upload, the client will publish that reading to the broker using a topic. Like we said before, topics are sort of like URLs or a file system. They use slash delimiters and text categorization. So much like you would sort your personal documents into folders like so, or a work document like this, topics have a hierarchy. Let's say you have a factory like this one, and you wanted to make temperature sensors placed on the HVAC units of each floor in your building publish their temperature. You could set up your topics like so: sensors / floor / temperature / HVAC ID. So the third floor main AC would be publishing to a topic like this. The 10th floor boiler would have a topic like this. And the 4th floor heater would use a topic like this. While there is no requirement that we organize our topics like so, not doing that is akin to putting every document you make on your computer desktop. You can do it, but it makes it really hard to keep track and makes it really hard to find stuff later. Most brokers require that you set up your topics ahead of time and will not let clients publish or subscribe to non-existent topics. This is good for avoiding typos and corrupted data, but sometimes you can set up your broker to be more flexible. Whenever a publication comes in for a topic, that topic will automatically be created. And this is good when you have a dynamic sensor network with new nodes joining without warning. Likewise, any client can subscribe to a topic the broker has, and a broker will send an error for that topic if it does not exist yet. An MQTT client publishes messages to a topic by sending the message and the topic to the broker. The broker then sends that message to all the clients that have subscribed to the topic. That's it. That's how MQTT works. Using the topic model, you can do a lot with a little. For example, you can develop MQTT clients to only use specific topics to publish and subscribe to when you want to have configuration changes, not just data. One thing to note is that topics don't have strict typing built in. There's nothing stopping a client in this factory's temperature network from uploading a binary cat photo to the temperature topic. This is unlike REST, JSON, and XML, where you can have more control over data checking. Now, you can add code to your MQTT broker that will scrub bad data out for you, but it's not built in. And this is one of those trade-offs of a lightweight protocol. There is one clever trick that MQTT brokers and clients can do that you can't do with REST. You can subscribe to any part of a topic. So maybe you want everything at a location, or maybe just sensors on the 3rd floor, or maybe just a specific temperature sensor. You can use wildcards in your topics to get just what you want. The wildcards available are plus or hash. Here's one example. This topic has a single wildcard plus. This would let you monitor all of the temperature sensors on the 3rd floor. But you can get even more advanced with subscriptions like this topic, which has 2 plus wildcards. This would let you get all of the temperature data on all of the floors of the HVAC units that are publishing to the temperature topic. And you'd get updates anytime one of those sensors were published. A plus wildcard is used to get a single level of hierarchy. The hash symbol can be used as a topic wildcard for all remaining levels of hierarchy. So for example, if you wanted to subscribe to everything going on all of your floors, you'd use a topic like this, and it would match any level of hierarchy after sensors. Or maybe you want to listen to all 10th floor sensors, you would use the hash wildcard like so. Depending on your type of data and the underlying transport, you may have different requirements for how reliable you want MQTT to be. More reliability means more data transmissions and more code management. Quality of service is managed by the broker, but the client can request a certain quality of service. Quality of service 0 is fire and forget. The broker and client will deliver a message once with no confirmation. Here's an example. You have a GPS vehicle tracker that sends location data over cellular every 30 minutes. If your tracker is running over a long period of time, it might leave cell network coverage. But it's okay if once in a while a GPS location is dropped. You just want to get most of the messages, so you have an idea of where your truck is. Quality of service level 1 means delivered at least once. The broker and client will deliver the message at least once with confirmation required. So let's say you have an IoT AC unit that is monitored and controlled remotely. When you send a message for it to turn on, you want to make sure it really turns on. If you send a message and the transport fails, you can just keep sending messages over and over until you get a reply from the broker. This quality of service is what most people use with MQTT. Quality of service level 2, deliver only once. The broker and client will deliver a message exactly once by using a 4-step handshake. Now this one is not as common because it's actually very, very hard to guarantee single delivery without a rock-solid transport. So you might want to consider a feedback system and a lower quality of service instead. But let's say you have a robotic tractor and you want to send it commands like move forward 50 meters. You want to make sure that you don't accidentally send 2 messages and it turns out it moved 100 meters, or no messages and it moved 0 meters. So that's where you'd want quality of service 2. Technically, there is no base requirement for an MQTT broker to store your published data once the subscriptions have been sent. But you can request or configure retained messages with your broker. This means that the broker will have a copy of a published message even after it was sent to all subscribers. If a new subscription is made by a client to the topic and it matches a previously and retained message, that will be sent as well. This is handy when a topic isn't updated that often, but you're adding new clients that are subscribing to the topic later. For example, you have an MQTT control light bulb. It receives messages whether to turn on or off. But what if it gets disconnected? Well, when it reconnects, if there's retained messages, it will receive the last publication, so it'll know whether it should be on or off by default. A client can set a clean session flag with the broker. That's like a clean start if you want to start from scratch or not. If that flag is set to false, the connected client is considered durable. This means that when the client disconnects from the broker, all of the subscription store and all of the quality of service messages will be kept until it connects again. If the session is clean and marked as true, all subscriptions will be removed when the client disconnects, and it will begin a new MQTT connection completely from scratch each time. The last MQTT detail we will cover is the last will. That's why it's last. This is sort of the opposite of retained messages. So let's say one of your MQTT client connects to the broker and on that connection provides a will publication. When the client disconnects, that will publication becomes a predefined message that is sent to all subscribers. Wills have a topic and a quality of service. It's basically just a preset publication. It's triggered whenever the broker stops hearing from a client. A good example is if you have an IoT relay that controls some machinery. It may be that if the MQTT controller client disconnects, the safest thing to do is to turn off the relay. So that last will publication for the controller should be an off message as a safety feature. There is one more option you can use, CoAP. CoAP is a little like REST, but it's pared down to be as light as MQTT. Like REST, it has get, put, post, and delete to URLs, but unlike REST, it has a very light and simple packet structure, and it's designed to be as minimal as possible, with binary data representation for commands and data whenever possible. MQTT uses the idea of a session or continuous connection, whereas CoAP, like REST, is sessionless. Data is sent and requested at any time. That means you could run CoAP on a transport like UDP, SMS, packet radio, or satellite where it's hard to get immediate responses. Like REST, a CoAP server doesn't manage many client message routing. Each client connects the server and sends request data. But like MQTT, the client can become an observer to get frequent asynchronous updates to a topic of interest. And in that way, it's not polling like traditional REST. Now, about that stateless connectivity. On the internet, CoAP usually uses UDP, but that can be a problem with firewalls. They often block individual random packets over UDP, and they only permit outgoing TCP connections. Now, you can run CoAP over TCP, but it isn't as common, and you sort of lose the benefit of having stateless UDP. This is most relevant when running on cellular and Wi-Fi, where you've got a direct internet connection. Another downside is that since each message is standalone, you cannot have any packet fragmentation. Each message must fit into a single Zigbee, UDP, Sigfox, etc. packet. The biggest benefit to CoAP is it's similar enough to REST that you can use it to easily transfer data between a web application and your IoT device, because in theory, they're supposed to be interoperable. And there's more stuff built into the CoAP protocol for data formatting and resource querying. But we don't see CoAP used very often, so it's hard to say if people are really taking advantage of this protocol. For all these reasons, MQTT has become one of the most popular, if not the most popular choice for protocols for IoT, followed by REST and then finally CoAP. There's a few other protocols that you might bump into on your IoT journey, but we covered the big three: HTTP REST, MQTT, and CoAP. Even though protocols and transports are two layers of your IoT network, they aren't completely independent. In particular, you'll likely be using REST whenever you have a transport that has high bandwidth and speed, like Ethernet, or when your transport is internet connected and talking to online services. MQTT is most often used when your transport has battery, bandwidth, or packet size restrictions, like Wi-Fi or cellular. And finally, CoAP is there when you have low bandwidth stateless connections like LoRa, Zigbee, or Bluetooth. Once you've picked your transport and protocol, you can then take the next step and start sketching out your IoT network. That will mean determining what services you will be connecting to, if any. And until then, arrivederci, auf Wiedersehen, and goodbye.